Thank you. All right, y'all ready? So we're going to talk about scientific notation in conversions from imperial to metric and metric to imperial. So I thought I'd start out with, again, a little story. You may or may not know this, but we actually have put several probes on Mars. So we've launched out some little spacecraft that have come to Mars and landed on Mars and driven around and taken pictures and things like that. But when we did that, I say we as, I guess, people, humans, the first thing we did was we sent out a probe, and the idea was that this probe was going to go to Mars and go into an orbit around Mars and start taking pictures and trying to find a place to land and things like that. So in the very beginning, we had sent one of these probes out to go into orbit, and we sent it out, millions and millions of dollars, and it basically didn't do that. It just went and crashed right into the surface of Mars, and we lost it. And they were trying to figure out what happened, and it turned out that there were the engineers that were working on this probe, or this orbiter, were both from the US and from Europe. And there was some problems in the code, the actual computer code, where they did not convert from US to metric or metric to US, and that's what caused the problem. So conversions are a big deal, right? In this case, it cost them an entire mission was lost because of it. So we are going to do conversions, but we're not going to spend too much time on it. And why aren't we going to spend much time on it? Because we have technology, right? So I'm going to use my phone right now. Convert 27.5 miles into inches.
27.5 miles equals 1,742,400 inches.
There we go. That's how easy it is nowadays, right? Like you used to have, you know, there was like a website that you would go to that you could like download, or not download, like drop down menus and convert. You don't even need that anymore. You can just speak to your phone and get a conversion. So realistically, in the real world, you know, even in the medical field, you know, there's apps that doctors use that they can convert. But what we do want to know is just how do we do it by hand, just so we can get it, you know, get a few of them out of the way, and then we will proceed. All right, we won't spend too much time on this. I don't know how I'm going to do this on the test. We'll figure that out later. All right, so we start this out with scientific notation. So scientific notation is just another way to write numbers. When we're dealing with chemistry and physics, numbers get really, really big or they get really, really small. And so instead of having to write a bunch of zeros, we just have notations for special notation for it. So this first number, 35,400,000, the decimal point is right here. To convert that to scientific notation, what we want to do is move the decimal point all the way to the left and put it right there, right after the first digit, right after the 3, that's where we want to move it. Okay, so to do that, we would have to do, let's see, 1, 2, 3, 4, 5, 6, 7 little jumps of the decimal place. All right? So if we actually move the decimal point to the left 7 places, the way we would write this in scientific notation is 3.54. Okay, so 3.54. And then all these zeros we're not going to write. We're instead going to write times 10 raised to the 7th power. And that's scientific notation. And don't get all, when I first learned scientific notation, I was like, what's that 10 to the 7th? What is that? Well, 10 to the 7th, if you were actually do that on your calculator, 10 times 10 times 10, 7 times, you would get this number. 1, 2, 3, 1, 2, 3. You get 10 million. All right? That's what you get. That's what 10 to the 7th is. So what you're doing is you're taking 10 million and multiplying it times 3.54, and if you did that, you get back this number. All right? It's just a condensed way of writing a big number. Now, if we have a number that's very small like this, 0.0000, a bunch of zeros, and then, like 9876, we're going to want to move the decimal point this time to the right. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9 places. We just want to have a single digit before the decimal place. So we moved it 9 to the right. So what we're going to write now this time is 9.876 times 10, but this time what? To the negative 9, because we moved it to the right. So negative 9. So 10 to the 7th meant multiply by 10 million. What does 10 to the negative 9th mean, though? We don't really need to know this, but just so you know, it means you're dividing. So it's this number right here really means 1 over 1 with 9 zeros. So 9 zeros here. 1 divided by that really, really tiny number times 9.87 gives you a really, really tiny number. So that negative means division, the positive means multiplication. All right, now that's how we convert from a number to from decimal to scientific. We need to be able to go the other way also. So the other way, here we have 2.32 times 10 to the 6th. So is that a big number or a small number? It's a big number because it's a positive 6. So what we do is we're going to take 2.32 and we're going to take that decimal and move it 6 places to the right. 1, 2, 3, 4, 5, 6. We'll place it here and we'll put zeros everywhere we didn't have anything. And that decimal is gone now. So what is that number? 2,320,000. So 2.32 times 10 to the 6th power is 2,320,000. And then this number is a small number. We're going to take 5.2, move the decimal point 3 places to the left. So it goes here now, and we put a 0 here and a 0 here. So this is actually 0.0052. Is that good? Okay. You probably just want me to give you like a test with like 30 of those on it, and that's the whole test? Yeah? Okay. All right. That's it for that. Now, like I said, there's what we call the metric system, and then there's the imperial system. In the United States, we use which one? In the U.S., we use the imperial. Yes, the imperial. We use miles, feet, inches, right? So originally, at least what I've read, is that 1 foot was usually measured from the king. Back in, I believe, England, the king would put his foot out there, and that's 1 foot. Seriously. And so it changed a little bit, depended on the king. And that system is not a very good system. You know, you take a foot and then you cut it into 12 pieces, and that's your inches, right? A mile is 5,280 feet. So that's just, a yard is 3 feet, right? That's the imperial system, comes from the kings, right? Imperial. We, Americans, right, we brought that system over when we came over from Europe, right? Came up trying to escape the persecution, right? All the rebels wanted to leave, so we came here. We brought that system with us. But then back in Europe, they're like, you know what, our system sucks. And so they went to metric, and we just still stick with their old system. So if you go to Europe, everything's in kilometers and everything's in meters, and we're still here doing our thing. All right, so in the metric system, what's nice about the metric system is that everything is in increments of tens. You know, so if you have your standard unit, let's say you're trying to measure the length of something, then you use meters. So you have one, let's say, meter. And then if you multiply that by 10, you get what's called a decameter. You multiply that by 100, you have a hectometer, 1,000 kilometer, kilometer, right? That's a distance. And then a mega. And then you keep going. There's more words, but we got to stop somewhere, right? And then if you go smaller, if you take 1 meter and cut it into 10 equal pieces, then you get a decimeter. Cut it into 100 little pieces, then you're going to get a centimeter. 1,000 little pieces, a millimeter, micrometer, and keep on going, right? So what's great about it is that because it's increments of 10, all you're doing is moving decimal places. That's it, because our number system is base 10. For us, with the imperial system, it sucks, right? If you have 1 foot and you multiply it by 10, you don't get some new thing, right? Now, if you multiply it by 3, you get a yard, but 3 is a weird number to multiply by. So the metric system is base 10. It's very nice, but we don't use it. It's very unfamiliar to you, right? So like if I say you're driving 50 miles an hour, everyone has a good idea what that speed is. If I tell you you're driving 50 kilometers an hour, do you know what that is? Do you feel good about it? Is it slower? Is it faster? So I mean, that's the thing. We don't deal with that system, right? So we're not comfortable with it. All right. So those are the metric prefixes, and then you have the conversions. So here's how we convert things from imperial to metric and metric to imperial. And this is the most important thing. All right, is that 1 inch is 2.54 centimeters. That 1 foot we know is 12 inches, right? 1 yard is 3 feet. 1 mile is 5,280 feet. Mile is an imperial measurement. All right, a mile is imperial. It's like inches, feet. 1 foot is 0.0348 meters. 1 mile is 1.609344 kilometers. That's how we measure lengths. Right, so we'll practice with this, but those are the conversions. We're going to need those. And then area, an acre, right? Acre is something we deal with, right? If you buy a tract of land or something, it's so many acres. Well, 1 acre is 43,560 square feet. So a square foot is 1 foot by 1 foot. It's going to measure 1 foot, 1 foot. That's 1 square foot. So an acre is 43,560 of these. A square mile, so if you do a mile times a mile long each way, like make a square out of it, that's 640 acres. And wow, I never thought about that. Got a buddy who they have about 1,000 acres. That's more than a mile by a mile. That's weird. Okay. And then a square kilometer is 1,000 hectares. Hectares. All right. All right, those are measurements of area. And then we have finally measurements of volume. I think we talked a little bit about this last class, that if you measure the length of something, that's like 1 foot. If you measure area, it's square feet. If you measure the volume like a box, that would be cubic feet, and that's what these are. So these are conversions that are actually used a lot in if you're baking a cake or you're getting medication. Fluid ounces to milliliters, liters to ounces, liters to cubic meters, tablespoons to teaspoons, cups to tablespoons, blah, 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 blah. You don't have to memorize these, right? And then mass. So let's get to some conversions. Like I said, we're only going to do a few of these. So let's just pick one here. Let's do this one right here, number 5. 9.1 milliliters. So we need to understand what this is saying. ml. ml there. This is a metric unit. It's a metric unit. The M is milli, and then the capital L is liters. So 9.1 milliliters is how many liters? So there's a blank spot here. We want to know how many liters is that. Okay? So because it's metric, all we have to do is move decimals over. That's the great thing about metric. We're just going to move a decimal. The question is, which way do we move it? So we go back to our little chart here, right here. And we had, what was it, 9.1 milliliters? And we want to convert that to liters. So we go and we find milli here, right? Milli. And then we find liters. So where's liters on this chart? The basic unit. Here it is, liters, right? So if we want to go from here and we want to move this way, how many positions are we going to move? We're going to move 1, right? 2, and then 3, right? 3 positions. So that tells us how many places we're going to move the decimal. The question is, which way do we move the decimal? Left? Why? A milliliter is smaller than a liter, right? So if I have 9 of these, that should be a very small amount of liters. Or if you look at the table, if you're moving from this unit to this unit and you're going left, then you're going to move the decimal left. If you're going from here that way, you're going to move it right. So I'm just going to take this decimal, move it 1, 2, 3 places. I'll have 2 zeros in front, so I have 0.0091 liters. Is that pretty straightforward? Okay. Let's look at another one. Let's do number 6. So number 6, we're going to do 0.72 km, convert that to mm. And I'll need your help to tell me what that is, what those units are. What is km? Kilometers, right? So m, the basic unit, meters. What's g? Grams and liters. Okay. So length, volume, grams. What's gram? Mass. Okay. So we have kilometers to what? Millimeters. So m is the number in front here. Here k is the number in front. So I'm going to move, let's see, 1, 2, 3, 4, 5, 6 places to the right. So I'm going to take that and move 6 places. So 0.72, I'm going to go 1, 2, 3, 4, 5, 6, drop it here, put zeros here. So I have 720, 000. So 720,000 millimeters. Let's look at number 10. 10 is tricky, all right? 10 is tricky. What is this saying? 4 meters squared. This is a measurement of area. That is how many centimeters squared? So let's see, is it as simple as moving decimal places? It's not. So this is the first problem that we're going to do where you're going to see that we actually have to use a conversion factor. All right. So let's see if we can't handle this. So I'm going to write this 4 meters squared is the same as 4 meters times meters. Now I know that looks weird, but isn't that what meters squared means? Okay. Now I'm going to write that as 4 times 1 meter times 1 meter. Again, I know that looks weird, but do y'all agree with that? Yes? All right, somehow I need to get to centimeters. So what is the conversion to go from meters to centimeters? I'm gonna go back to my chart here. All right, so meters, centimeters, right? So if I have 1 meter, I have 10 to the negative 2 centimeters. Another way of saying that is that if I have 1 meter, how many centimeters do I have? I said that wrong. Hold on. If I have 1 meter, it's a measure of length, right? Let's say that's 1 meter. How many centimeters are in there? Because they're smaller, right? Centimeters are smaller because they're this way on the chart. So how many centimeters are in here? 100. There's 100 centimeters in 1 meter. So I'm going to write that down. 1 meter is equal to 100 centimeters. How many millimeters are in a meter? 1,000, right? How many decimeters are in a meter? 10. All right, so I need to know what this, we call this a conversion factor is. 1 meter is 100 centimeters. Now watch what I do here. This is going to be the tricky part. I'm going to take 1 meter, I'm going to write 1 meter over 1 meter over 1. Just follow me first. Now what I'm going to do is multiply this by this conversion factor. So what I'm going to do is take, I want my meters to go away, don't I? And I want to create centimeters. So what I can do is I can put 1 meter on the bottom here, but what's 1 meter in terms of centimeters? 100, so I can put 100 centimeters on top. So it's like this is a proportion. There's 100 centimeters in 1 meter. Then over here, I do the same thing. Now, why did I do it twice? Because I have to cancel each of the meters out. So notice what happens here is this meter and this meter cancel. This meter and this meter cancel. And what am I left with? Centimeter, centimeter, which will be centimeters squared. So I'm going to have to take the 4, multiply by 1, by 1, by 100, by 100. And then divide by 1, 1, 1. So I'm really just going to divide by 1. I know this seems a little weird first time, but after we do a few, I think you'll hopefully pick it up. So what do I have? 40,000 centimeters squared. So that's just 4 times 100 times 100. I guess the danger in this problem is that if you look, okay, hey, I'm trying to go from meters to centimeters, and so you just go, meters over to centimeters, you think you move the decimal point 2 places, that's not what happens. Because it's a square unit, you actually have to do it twice. And so you get 40,000 instead of, 400? All right, should we do another one, or you all okay with that? All right? All right. Let's do something that goes from like imperial to metric or metric to imperial, and then you'll see this in action again. Here we go. There we go. 21.5 inches is how many centimeters? 21.5 inches is how many centimeters? .5 inches is how many centimeters? So we're going from inches to centimeters. Inches is imperial and centimeters is metric. So I actually need something that gives me that conversion. So I have to go to a chart. And somewhere on here I have it, right? There it is. I have 1 inch is equal to 2.54 centimeters. You all okay with that? Okay, so I'm going to use this. I'm going to use this to do my conversion. So I start out by writing out 21.5 inches over 1, and we'll always create a fraction out of it. And then I want my inches to go away, don't I? So I multiply this by another fraction with inches on the bottom and centimeters on top. And that's this equation right here. I can put the inches over the centimeters like this, or I can do the centimeters over the inches. And it depends on what we're looking for. So in this case, I want centimeters on top, so I put 2.54 on top and then 1 inch on the bottom. Y'all see how I'm using that? Okay. And now your inches will cancel. And so the multiplication we're going to do is 21.5 times the 2.54, and our answer will be in centimeters. $54.61. All right. (21.5 inches to centimeters).
21.5 inches equals 54.61 centimeters.
Okay. That was a lot easier, right? But this is the actual math that we're doing, right? Okay, we just want to make sure we understand how we would get that if we didn't have this. Maybe one more, and let's do something that has a square unit or something on it. Yeah, number 8 looks good. Number 8's a good one. .5 cubic feet to cubic inches. So 0.5 feet cubed equals how many inches cubed? That's what I'm doing. Well, we're trying to go from cubic feet to cubic inches, right? So we need a conversion factor that gets us from feet to inches. Do we have that? Do we know anything? Okay, what do you know? 12 inches is equal to 1 foot, right? All right, now we can't use that straight away because we have cubic feet over here. So what I'm going to need to do is write down 0.5 times feet times feet times feet, because I have 3 of them, right? Cubic. Now that's the same as 0.5 times 1 foot over 1 times 1 foot over 1 times 1 foot over 1. So you see I'm accounting for each of the cubic feet. I need to get rid of 3 feet units in here, right? This one needs to cancel, that one needs to cancel, that one needs to cancel. So that means I need to come in here and multiply now by conversion factors that have feet, 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 right? And on the top, inch, inch, inch. That way I get cubic inches. And now I use these numbers. I have 1 foot is 12 inches, 1 foot is 12 inches, 1 foot is 12 inches. And that's how your feet are going to all go away. So you're going to do 0.5, don't forget the 0.5. 0.5 times 12 times 12 times 12. 364? No. 864. I heard 364, sorry. 864 cubic inches. There we go. Questions on that? You all sure? You're awfully quiet. All right, 11, 12, 13, 14 are a little bit different, so I think they're worth looking at. Let's look at number 14. Does anybody recognize 186,282 miles per second? That's the speed of light. Think about that. That's pretty fast, huh? 186,282 miles every second is the speed of light. So what we want to do is convert miles per second into meters per second. So we have two units going on here. Miles per second, miles is a distance, second is time, isn't it? We want to convert that into meters, which is still a distance, and then seconds, which is the same, right? Meters per second. So you know what? Let's change this. Make it more interesting. Let's go meters per hour. That'll be a more interesting problem. We want to convert miles per second into meters per hour. With me? All right, so what I'm going to do is I'm going to write down 186,282 miles. Per means a fraction per 1 second. Does everyone understand how that first piece of information is this proportion, this ratio? Now we want to get that to meters, right, per hour. So we've got to find a way to convert miles to meters. And we also have to convert seconds to hours. So I'm trying to come up with my conversion factors over here to help me get from miles per second to meters per hour. So do we have anything in our notes in those tables that get us from miles to meters or meters to miles? Is it there? What do you have?
You convert miles to feet and then feet to meters.
So you have to go miles to feet first? There's nothing that goes miles straight to meters? Or meters?
Kilometers.
Yeah, so no, we have to go, okay, so this is trouble. We don't have anything that goes straight from miles to meters on our table. Now, can we convert from seconds to hours? You have to know how many seconds there are in an hour, though. So how many seconds are in an hour? What is it? How many seconds in an hour? 3,600. Why? There's 60 minutes in an hour, right? And how many seconds in a minute? 60. So you're going to do 60 times 60, which is 3,600. So there are 3,600 or 3,600 seconds in 1 hour. So this conversion factor we actually have, I think, if not. Yeah, think about it for a little while. But miles to meters we don't have. So can you tell me what we did have? We had miles to what? We had miles to feet. So miles was, 1 mile was 5,280 feet, right? And then we also had that, what about the meters in feet?
Oh, 1 foot equals
1 foot is
0.3048
0.3048 meters. Meters? Meters. Okay. Y'all understand what I'm doing? Okay. So now we come over to this, and we're going to start multiplying by conversion factors. Let's take care of the seconds first. Let's get rid of the seconds. So where are my seconds going to need to go? On the top or the bottom? On the top, because seconds is on the bottom here. I need seconds on the top. And I'm trying to get to hours, so I put hours on the bottom. And I'm going to put 3,600 on top and 1 hour on the bottom. So you see how I've inserted this into this to get my seconds to go away. Y'all good with that? Now, I need my miles to go away, and I need to turn it into meters, but I can't get there straight away because I don't have anything go straight away, straight from miles to meters. But what I can do is I can go miles to feet first, can't I? So I'm going to insert next to this something here, and I need what down on the bottom? Miles, so that it will cancel. Miles will cancel with that miles, and up here I have feet. So 5,280 feet in 1 mile. That will get my miles to go away. But my answer right now is in feet per hour. And I don't want feet per hour, I want meters per hour. So now I need to see if I can get rid of the feet and turn it to meters. So I multiply again by another conversion factor, and this one's going to have feet on the bottom and meters on the top. And that's the second one right here. So 1 foot is 0.3048, I'm out of room, meters. And cancel out the feet. So at the end of the day, I'm multiplying this number times this number times this number times that number. And then I'm dividing it by 1 times 1 times 1 times 1, which is just 1. So just multiply those 4 numbers across top. Who has that for me?
They give me a scientific.
It's big, right? Scientific? Okay, what's the scientific?
1.07792505.
Okay, good enough.
Times 10 to the 12th power.
Times 10 to the 12th power. Did you not get the same thing? You got the same? Okay. So that's the number it gave you. Now that means you would have to move this decimal place 12 places to the right. But that's a big number, and that's going to be in meters per hour. That's a bit involved, yeah? Don't you think? Should we see if Google can handle that? Where the heck's my phone? Oh, there it is. Let's see if Google can handle that. 1,008, oops. User. 186,282 miles per second into meters per hour. Had some trouble. So it had some issue. It didn't give me a result. Let me see if I did it right. No, I did not type it in right. There we go. Okay, it got it. It picked up an extra word there in the front. 1.07925055 times 10 to the 12th meters per hour. So this is almost a little obsolete at this point to need to do this, right? But I think the mechanics right here, if you ever have to take a chemistry class, I know most of you are not chemistry majors, right, or getting into the STEM field, but if you ever had to take a chemistry class, you'd have to do a lot of unit conversions and stuff like this, and a lot of this cancellation. So, you know, you never know, you might change your major. I want you to at least have seen how we set proportions or use proportions to do cancellation of units and conversions. All right, we're moving on. I'm guessing you're going to have some questions on that homework. So we'll start class on Wednesday and with questions because there's a lot of little word problems in there, and let's just see how you do on it. I would encourage you to try and do as much of it by hand, and if you have trouble, you know, go to the internet, go to your phone, see if you can get the result. We're kind of really going to change gears now, and we're going to start talking about graphs of lines or linear equations. And before we do it, I try, if I can, to motivate the idea a little bit with something more real world. But, because then you can kind of see how this would tie into something that you see every day, maybe. I don't want to ask anyone here how much they make, like if they work and how much you make per hour or anything like that. So I'm just going to make up a situation, all right? Let's say that Sam works at a car dealership, all right? Sam has a base salary of $3,000 a month. All right? I'm totally making this up. I don't know if that's how much, I doubt, whatever. I don't know. Just making it up. Sam works at a car dealership. Sam has a base salary of $3,000 a month. Sam also earns 3% of each car sale. Yeah, let's change this. This is going to be more complicated than I want. Let's make it, he makes $300 for each car sale. So for every car he sells, he's going to get $300, regardless of whether or not it's, a $5,000 Toyota Corolla with 100,000 miles on it or the brand new, whatever they've got in the showroom. No matter what car it is, he gets $300. I'm pretty sure it's not the way it works, but just for the sake of this, let's just go with that. Okay? This is actually, you can model Sam's income with a linear graph. And that's what we're going to look at, linear graphs. So let's try and put together how much Sam makes. All right, so let's say his pay, we'll call it P for his pay, is equal to what? So how much is Sam going to make per month? As long as he shows up to work and he's not, slacking off, they're going to pay him $3,000 no matter what. Just show up, do your job, right? $3,000. Plus what? $300 for what? Each car he sells. Now, we don't know how many cars he's going to sell, right? So we'll call that, I don't know, X maybe, right? This is what we would refer to as a linear equation with two variables. Not one variable, two variables. We have X in here and we have P in here, right? Now, normally what we're going to look at in here is we're going to make that Y, and so we're going to graph this as a line. But in terms of this problem, I put P there because it's his pay, right? So if we were to try and get some sort of graphical representation of what's happening here, if we put down here X, which is the number of cars that he's going to sell, and P here as being his pay, then what happens if Sam sells 0 cars? He's going to make $3,000. So his pay will be $3,000, right? No cars sold that month, $3,000. What if he sells 10 cars that month? So he's going to make 3,000 plus 300 times 10, which is another 3,000, won't he? So he's going to make 6,000. Agreed? Like that. And then what if he sells 15 cars? All you're doing is going to replace that with 15, right? Put it in there. So how much would that be? 7,500? Something like that. So it would be somewhere around here. And what we get is that if you were to plug in all the different numbers you could plug in, you would get a graph. If you put all the points, like all of these points in there, you get a straight line. Right? So this would be a linear representation of his income. So more cars he sells, more money he makes, right? Also in this problem, does it make sense to have negative numbers? No, right? He's not going to have negative sales. So this graph would only really make sense this way. All right, so that's what this section is about, is we're going to be given these linear equations in two variables. What we want to be able to do is graph them, be able to draw a picture of what it is that we have. I know all of you have background with this. I'm sure you've seen linear equations. Is it safe for me to assume that? Okay, all right. So let's look at this first one. So we have this linear equation. Notice it has two variables, x and y, and you're asked to find the x and y intercepts. So we didn't talk about that, right? We didn't talk about what an x and y intercept is, because I started you with that word problem. But if you were to have a graphical representation of a line, then that line is going to most likely hit the x-axis somewhere, the x-axis, and it's going to hit the y-axis somewhere. So this would be our x-intercept, and this would be our y-intercept. This all look familiar? Yep. So with linear equations, we have a method, a set of steps on how to find both the x and y-intercepts. So can anybody tell me how we find the x-intercepts for a linear equation in two variables? You set y to 0. So what we're going to do is set y equal to 0 and then solve for x. The reason we do that is because on our graph, if we're trying to find that point, notice that the y has to be flat right here. It has to be 0 in order for us to be on this line. So that's why we set y equal to 0. So all I'm going to do is just rewrite this equation, replacing the y with 0. And now you have a linear equation again, but with one variable instead of two. And so we can solve that for x. So if I gave you time to solve this, you would get it. I'm not going to actually go through it. You get negative 4.5. No, positive 4.5. Is that all right? That's how we find the x-intercept. How do you find the y-intercept? You do the opposite. To find the y-intercept, you set x to 0, and you solve for y. So I go y equals, if I let x be 0 here, it's gone, isn't it? So I just get 9. So y is 9. So if that x is 0, this negative 2 piece just goes away. So y is 9. That's all it asks for, right? That's all it asks for. So what we could do, even though they're not asking for it yet, we will need to do this later, is we could actually graph this line now. Because we know where it hits the x-axis at 4.5. So we could draw 1, 2, 3, 4, here's 5. So 4.5 is where it hits the x-axis. And it hits the y-axis at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. And then once you have 2 points on a line, you can just draw a straight line through them. So we have a straight line that connects these two. So that would be the graph. That would be the graph of that line. You feel like you could do 2 on your own? Yes? Let's look at number 4 because it's a little more interesting, I guess. Not too much, but why don't you take the next maybe 3-4 minutes. Try and find the x and y intercepts for this. They're going to be decimal, so you need your calculator. And then see if you can't just draw a quick little graph of that line, all right, for number 4. That fair? I'll leave that up there. I'm also going to pass the sign-in sheet around. Sometimes when we take quizzes, I won't, but I'll do this today. Remember, our first exam is next Wednesday, right? Okay, I have the solution, I guess, up here. X-intercept should be 2.125, y-intercept should be 3.4, and then here's my, rough